Hey guys, good morning. This is Professor Nehru, Department of Aerospace Engineering, SNS College of Technology. In the flight dynamics course, today we are going to see the what is the dihedral effect. What is meant by dihedral effect? Usually, we will see the design of airplane. There we'll understand the where we have to fix the wing with the respect to the fuselage. So, in the context of the aircraft flight, the dihedral effect is the phenomenon of roll moment created by the side slip. So, usually in aircraft we have the three moments. One is pitching moment, rolling moment, and yawing moment. Here to understand the phenomenon of rolling moment by keeping the aircraft wing in fuselage in certain location. So, the dihedral of the aircraft is largely affected by its dihedral angle. Once you fix the aircraft either dihedral or anhedral based on the root chord to the tip chord, so which is the angle of deflection of the wing for level in roll of the airplane. So dihedral angle of an airplane is the upward angle from horizontal of the wing or tail plane of the fixed wing aircraft or airplane. So whereas an anhedral angle is a name given to negative dihedral angle, that is when there is a downwash angle from horizontal of the wing or tail plane or in the fixed wing aircraft. So it is the angle between root to tip of the aerofoil or the wing where you can understand the dihedral position of the wing. The main purpose of the dihedral wing is with this dihedral wing where we can change the angle of aircraft wing from the wing root to the wing tip. There are almost the total amount of dihedral determines the amount of inherently stable or stability along with the rolling axis. So when we see this picture, we can observe the position of fuselage and the wing from the lower part, that is starboard and port side. So this is the tau is the dihedral angle. When this low wing configuration, we have positive dihedral, and second figure shows the dihedral angle is a 0. So there is no such difference between root chord and the tip chord position, whereas the third one shows the anhedral is a negative angle of attack, that is a negative dihedral angle tau. So here the position of fuselage and the wing will vary with minus dihedral angle. While seeing this rectangular straight wing, leading edge and tailing edge, where the free stream velocity hitting the wing with V infinity with a beta angle, whereas resulting of V sin beta and V cos beta. So this V sin beta and V cos beta uh, will change with respect to the dihedral angle and the sweep angle, whereas the tau is the sweep angle. So dihedral effect is the angle at which the wings are slanted upward from the root to tip. Dihedral stability affects in the results of slight side slip which occurs when one wing in the force down. So the side slip create a difference between the angle of attack of the upper and lower wing, with the lower wing have the greater angle of attack, which creates a more lift and arise the lower of wings. So from this diagram we can see this center of gravity acting in the fuselage, and both sides of the starboard wing and port side wing are producing same amount of lift, whereas this is a straight and level flight. Where when the aircraft is banked or turned to the starboard side or port side, one side lift will be in vertical and another will increasing the angle. So this time this rolling moment can be balanced in both banking and rolling will be highly stable in balanced flight. So there high angle of attack and low angle of attack, this condition helps to understand whether we can avoid the rolling moment of aircraft by increasing the dihedral of the angle of the wing. So another example, we can avoid the rolling moment, the large angle of attack alpha in locally, and the smaller dihedral angle. So upper wing have the high rolling moment, whereas the which can avoid by placing the wing on top, whereas in the lower angle of attack or lower wing configuration, rolling moment will produce more rolling. So which we understand how this dihedral works. So higher angle of attack and lower angle of attack, lift will be very high, whereas in lower angle of attack lift will be low. This can be counteracting the rolling moment by the external induced relative wind. Both higher angle of attack and lower angle of attack, the high lift and low lift will be compensated. So here we have the different types of wing position and configuration. So first one is no dihedral effect. This is a rectangular straight wing, and second one is straight dihedral. Third one is tip dihedral, and fourth one is polyhedral. These are the helps to control the lateral stability of the airplane. From recalling the stability criteria, we have to the rate of change of rolling moment should be reduced with respect to the angle of attack or the dihedral angle. So rolling moment created by the side strip roll airplane to the large rolling angle could be graphed between side strip beta versus lift coefficient CL. So this will be usually negative with respect to the changing of angle. So what is a sweep angle? This once we obviously understand the what is a dihedral and anhedral, then we need to understand what is meant by a sweep angle. This is also similar pattern to the wing position, whereas in the longitudinal changes of wing position. So by understanding the bird's design, the narrow tapered wing and lower elegant wing and back pointed wing and short rounded wing, feathers, fingers, and massive wingspan. These are the different nature birds are having the sweep angle of the wing. There's a swallow bird, terrans, falconer, albatross, eagle, and sparrow. So these are different wingspan and sweep angle are designed by nature, and from this we can understand how much the sweep angle influencing the flight performance and the stability and control of the airplane. So now we'll see the another changes of position of the nature during loiture, transition, or the strike condition. So one is this loitering and transition and strike condition. The wings are varying its position by adjusting the sweep angle. So once the wing platform is larger, it flies 31 km per hour. Once it start transition, it will fly 45 kilometers per hour. Once it gets shrink, then it will fly 80 kilometers per hour. This clearly explains the once the wing position and the sweep angle changes, the speed of the bird will increase. So for subsonic to transonic, transonic to supersonic, the design of aircraft, we need to understand what type of wing we have to use, whether a straight wing or a sweep wing or a low aspect ratio wing or a very delta wing. This concept were arrived from this wing position by adjusting the sweep angle. So this is the sweep angle from the fuselage root to tip or the root card to tip card. There may be a different angle or the increasing of position from root card to tip card. The position will be vary. It's not in the straight line. So here we have the sweep angle of 25 degree. So tip card percentage is 20 of root card and tip 20% of tip card. So this is the mean card, right, for the wing. So rectangular wing, the lambda will be 1, whereas stall position, progression, and higher taper ratio, where the lambda is equal to 2.0, 0.25, and if it is a sweep, then the position of stall progression will differ. So for this only, we are changing the sweep angle and we are changing the stall progression from root to tip. So this we have understanding the what is the dihedral, what is the anhedral, what is the sweep angle, and remaining thing we'll see in the next class. Thank you.